Welcome back to part 4 of the Precession series. Now, if you haven't watched any of the other videos, I would urge you to go back and watch them first, because this video deals with some of the questions that people have raised about Jim's model. So, without further ado, let's dive in and get some answers to those questions. Okay, so let's start at the top and in no particular order. And I think some of these might overlap, but we'll kind of cross that bridge when we come there. So the first question or set of questions is from Don Kress, and so he starts off by asking, it'd be quite interesting to discuss for the upcoming Q&A regarding the cyclical extinction events, and in particular their timing. Identifying the cause will likely be more difficult and may need to wait until more data can be gathered. So this is I guess the question: can we relate the mechanism of the turning, so the how you would describe precession by following the filament and moving in and out, to some sort of cyclical extinction cycle?
Right. I think that the starting point there is that we know from every astronomical cycle that we do know, the yearly cycle, the daily cycle, the lunar cycle. We know that they affect us in all these different ways, and even more, they're finding out every day. What we lost, though, is first just that there were longer cycles. But once we get those down, then we can begin to see which ones affect us in what way. We at least have the cycles down. The actual the periods actually can be calculated first, just by that.
So by that you mean how long it takes for us to do? I mean, I guess the obvious one is obviously what used to be termed the precession cycle, so completing one rotation, and then further out would be there would probably be greater cycles, because we did talk originally in the video about the I think it was 26 million years to do one rotation. But thinking about the structure in more detail in my head, I can see that there would be, as we follow around, that our path would sort of spiral in and out. So there would be, I'm guessing, cycles within that 26 million year cycle, which would bring us closer in and then potentially further out and closer in and further out. As well as, I think his second point, I think, also relates to that whole cycle thing, is that when you look at the, he says, also since the plane of the solar system is tilted with respect to the plane of the galaxy, do the upwards and downwards transitions through the planes of the galaxy result in different interactions with the current flows? So this is something that we talked about. So the crossing in and out, does that cause disruptive events, which we would also have as another cycle within that?
Yes, well, the orbit around the Pleiades would match the mainstream's 26 million year mass extinction cycle, but even they put the correlation to us crossing through the galactic plane as maybe being significant in that. So that we just would have a different orbit up and down through the plane, but that period is one that the mainstream's looking for, and they've kind of got to guess that it has something to do with that motion through the galactic plane.
But that would be another time cycle as well, different from the 26 million, different from the precessional one. That would be layered on top of that whole system as well.
Well, that would be like the 26 million year cycle, that their mass extinction cycle. See, they have the precessional cycle, and that's more like what the Eastern Yuga cycle is. And they know that they're starting to put effects on that periodicity, like ice ages and things, and that they're trying to map to more or less that time cycle too. And then on the
Okay.
26 million year cycle, they have the, the hard mass extinction cycle.
Yeah, I don't think the next bit is about carbon dating, which I don't think is really relevant to the model itself.
Well, no, except that it does bring up, and if you're willing to accept that ancient people had these knowledges of that they could use as calendars, just world ages and things like that, you might suspect, if you're open to like that idea of ancient knowledge or technology, like Chris Dunn argues with the pyramids construction. If they had that kind of knowledge, then they might have also stumbled on the idea that radioactive decay rates aren't a constant, and fossilization might not work the way they're not going to likely have made all the same errors we made, so that they would have figured out too that the right calendar on there is a right calendar to use on each scale. That's
right.
If they were aware of these cycles and they knew how constant each of them were, then those become the natural calendars then for that cycle. For example, if there were catastrophic changes in the solar system, then the best way to keep track of those isn't to use anything on the solar system then for a time marker. You can't use days and years. But if you jump out to a scale that is a little bit more consistent, then you can map the short-term changes in that timeline. And that's basically what you see that they were actually doing. And that's why the precessional cycle was so important to them, because then they could describe when these catastrophic changes would even happen in our solar system based on that bigger picture.
Yeah, so being able to predict it in a way that they didn't rely on, they used the calendar system or a way of identifying it that wouldn't change based on, those environmental changes.
Right.
Okay, so moving on to the next one. So this is from Karul. He says, one would think that the effect of this motion could easily be gleaned from sources that already exist, like astronomical data from an orbiting satellite or even the Hubble telescope, for instance, and it shouldn't be hard or take that long to detect the precession. So again, and he talks about comparing Earth-based photos and stuff like that. So this comes back to this, is there astronomical data that could help us to verify this motion?
Well, that actually goes to a lot of the work that Walter Cruttenden was doing, was showing that there's like almost overwhelming evidence, and he used the moon as an example and meteor showers to show that our whole solar system has to precess relative to distant galaxies, for example.
Yeah.
And the whole problem is that there's like a kind of a sleight of hands, is that the mainstream uses different reference frames for different types of calculations, and then it's easy to confuse yourself even into which one you're using. If you're using the solar system reference frame, you're not going to need to use precession, but you might not be aware that you're not doing that. And that's what he pointed out, is that they're actually doing a sleight of hands, that all the evidence though is that things are precessing. The whole solar system is precessing relative to the outside.
Yeah.
And the observational evidence is there. It's like almost, you don't see it because you don't have you're not looking for it. If your math works, if you've got a system tweaked to where the math works, you're not even going to challenge. It's only when it doesn't give you the right answers that you look for problems. But if your math is working, you don't always look at the sleight of hands that you did to make it work. And that's basically the dilemma in the first place.
I guess in theory, given enough time, then something like the Hubble telescope should be able to show that precession, that it is precessing as well, that when it observes the same stars, they are precessing just like on Earth, because as you say, it's the whole system. But I'm not aware that we have that data from Hubble, because I mean, how much time would you need in order to show that the data from Hubble is processing as well. But I guess that also depends on what you have as your zero reference frame. That's another problem, isn't it?
Right. That's the problem. If you're using for like if when they do like measurements of like relative parallax, you're using the background stars for a reference frame, and then you're looking at the motion of nearby stars, but then you've got an issue that they're all moving separately too, and then you're making the starting assumptions that they're not moving, they're not precessing, and then you're basing your star motions on that rather than
Yeah.
you end up in the same can of worms basically.
But effectively, there is data that does prove it, but the problem is that we're assuming, the mainstream assumes that we're on Earth, and therefore that data is only showing what we would expect it to show. Bar this, and we'll come back to that, stars that don't precess. But generally speaking, the assumption is that the whole planet precesses, and that's what we see in the data. And then the same for any of the Hubble ones. We assume that motion, and therefore everything is corrected for that, and therefore it's. I mean, I suppose in theory you could. No, you couldn't. You'd have to know how they zero that data, and we're not privy to that information at this stage.
Right. That's basically what Walter Crittenden looked into, is where they're in what cases they are allowing for precession, figuring that into their equations, and when they are not. And the whole idea is that they should be, if Earth is precessing, then they should be, anytime you look at anything outside of Earth, you should be allowing for precession. And they're completely ignoring that and only using that in for larger scale, basically in the larger scale picture.
Yeah. Okay. So the next question is back to Don here, and another question, and this one for me was a particularly interesting one. Is so he talks about if and this is to do with, I guess, the motion of us following the filament, and the fact that our system would flow through this Birkeland current. So he talks about the question of if you imagine that the stars, including our own, are part of the Birkeland current, and they are being dragged along that Birkeland current by the moving charge, then the current to power the solar system is being somehow provided by the Birkeland current, and that flows into and out of the solar system. And in order for this to work, the axis of the solar system would have to be somewhere between the inline perpendicular and the axis of the Birkeland current. And for me, I mean, we obviously don't know. We have no idea how we connect to the Birkeland current. But for me, the next bit was the bit that kind of got me thinking, which is to do with the drag. So again, assuming that our star system is flowing through the Birkeland current, that the question is, do we flow at the same rate as the plasma, faster than plasma, or slower than the plasma? And he specifically asks it because he's asking whether, if we flowed slower, there'd be a drag, and does that drag create part of the energy for powering our system, which I thought was quite an interesting analogy to have on that.
That's the hard thing to get with the orientation of our system. Now, the way that Donald Scott and Michael Claridge, for example, model it with the ecliptic plane being a cross section of the current. That I've taken the math of the Bessel function model to show that yes, you can explain the sun's spin that way. The faster spin at the equator compared to the polar region by matching it to that, and you can match this weird relationship of eccentricities and orbital inclination. In other words, like why Pluto's orbit is inclined and elliptical to the extent that it is. You can match all this to the Bessel function model, assuming current is coming pretty much through the ecliptic plane. Now, the main objection to that idea from the mainstream is they'll say that's not how we're moving through space. But again, that's the reference frame, and you have to see that the whole motion is complex. If our solar system is traveling along a filament, that filament is spiraling around another filament, then that's two motions already for the solar system, and so on. And then that whole thing is moving around the local chimney. And all of this, the whole spiral arm, of course, is moving. So it depends what reference frame you want to use, basically. And that's the problem. They're not, when the mainstream says that this is how our sun is moving, you have to say with respect to what? With respect to the galaxy, with respect to the local system of rest, with respect to the local filamentary cloud. See, they would have us moving one direction, but then this filamentary cloud that we're in or on is kind of blowing sideways across our path in their model. But that's actually what we want, is more our local motion compared to that is what's more important than how we're moving in the galactic or even in the local standard of rest. That, you know.
But in terms of if we are part of a Birkeland current that is flowing, is there any, in your mind, the way that it would work, would it be any difference to the rest of the material in that Birkeland current? So the plasma, I guess, that sits outside of our system, would that be traveling at any different speed to us?
Yeah, well, we know that again, just from mainstream observations, that there is a interstellar wind, and there's like a flow of neutrals through our solar system, and the interstellar wind of charged particles. So this would be the where you'd want to put the current flow. Once you realize that the sun is spiraling around the magnetic field, then you already see why you're not going to match the sun's direction of motion to the background magnetic field direction. It should be at an angle. We better see it at an angle to the magnetic field direction. Otherwise, there won't be any spiraling.
But would that, in your mind, would that mean, because if we assume that the Birkeland current is composed of, plasma material, so neutrals and also charged particles, as well as the stars, and our assumption would be that for the majority of stars that they would flow at a similar speed, is there a speed difference between the remainder of the material and us or not?
Yeah, like on the scale of like the local interstellar cloud, for example, we do have a motion relative to even to the filament on that scale.
Right. So in other words, that could be part of what is providing some of that energy, is that difference in movement, because in order for there to be an inflowing current, there has to be movement, and if we all move at the same speed, there can't be any movement.
Right, although technically you wouldn't have to have any. I mean, we could be parked in space as long. Yes, relative movement, like
relative. Yes.
Right.
I mean, you could also do it through magnetic fields. So flowing magnetic fields would also be a way of providing energy into the system. But I guess at this stage we don't, just to be really clear, we don't really know. And this is, one of the things that you've been kind of trying to look into is mapping that detailed scale from the smaller filaments up to the larger ones to try and understand how the movement and how the Birkeland currents sort of go up in a hierarchical scale.
Right, and unfortunately, the one that's most interesting to people is the one that flows right through our solar system, and that's the hardest one to map out. It's like definitely dark mode to us. Whereas if we jump up to the scale of the local interstellar cloud, we can see that these are filamentary gas clouds. Even the mainstream, wasn't originally looking for them, found that there's these filamentary gas clouds that star formation happens in. So, but down on the solar system scale, where we really have trouble, clearly we don't see a filament coming into or out of our solar system at all. So it's pretty much got to be dark to us, except again, from what we can learn on other scales, like when you see that the sun's current sheet takes the same forms as galaxy shapes, then you've got you've got a picture to go on just from where those shapes are clear.
Yeah. I think in his point, and I guess this is an interesting, because we've talked about the fact that moving closer into the center of the Birkeland current could have an effect, because obviously the magnetic field would be stronger as you move towards the center. But equally, one of the things he kind of points out is would our speed relative, or the charge density that surrounds us, if that were to change, then that too could, I suppose, in some sense, have an effect on the input current to our system, which again, I mean, without really understanding the structure of these Birkeland currents, it is foreseeable that some parts of the Birkeland current might be caused to accelerate at some stages versus others.
Right, and well, with the whole idea of that precession, like for example, the idea of precession, the rate of precession increasing. Now that's one where someone could do some follow-up work and just see which model works best for modeling that increase in the rate of precession. There's a lot of competing theories. The one we start with, that gravitational tugs of the sun and moon. Well, then you better explain why, with the moon receding from the Earth, why precession is speeding up. But you could at least attempt to model that if that was your theory. And there's some theory that, like the Binary Research Institute had, is that precession was caused by our gravitational elliptical orbit. Well, then again, you better match the rate of precession to the changes you would have in an elliptical orbit. Or if it's due to spiraling around a magnetic field into a stronger or weaker magnetic field, or spiraling on two scales, that's a whole nother way to model it. And since we do have pretty accurate data for how the rate of precession has been proceeding, that's the information's already there to distinguish between the models. But I'd let somebody else duplicate that, even if it's just to disprove that the mainstream's model.
Yeah.
See, I guess that's the first thing with precession to get out of the way, is that regardless of whether you believe any of these, anything that I've presented on that, just to see that the mainstream model doesn't work is already putting everybody ahead of the game. Just to challenge that and see the issues with that model, and you're already, at least you don't believe something that's not true.
Okay, so the next question, if we move on, which again is sort of related to what we discussed before, which is, can this model help us to match with past observations, and then also can it allow us to see things that might come in the future? And because I asked on what he meant when he said that, and he was really quite open about it can be anything. So the question is, does this model match, and for me it's really difficult to see how you would match this specifically on this model to things that have been in the past, and I guess looking to the future, would there be specific things that we would say, once we were able to map this fully out, this would be, in, I don't know, 10,000 years, we would be moving closer in to this filament, and that might have this effect.
Right. Once you see the time scale, like for the precessional cycle, then it is interesting to note that we see this convergence of stars in the direction that we're heading even now, and that it's supposedly around another 11,000 years from now, that the stars that we're traveling with are going to be converging on us. Is that a good example?
I mean, yes, because I think that, I guess part of it is, can we predict things for the future that, and maybe, 11,000 years is maybe a long time, but are there things that this model could predict which we could, test in years to come?
Yeah, see, the idea is if it really is just pretty much a gravity only model that we're talking about, then there's really no reason for anything significant to change with any points in the precessional cycle other than just the most mundane, how Earth is tilted towards the sun, and that would control the seasons, of course. But once you accept that this is all due to electromagnetic forces, now there's
the way I sort of see this is if we look at your classic astronomy software package where you can move forward and backwards in time, that model is only based on a gravitational model where the stars have a fixed velocity, and therefore you kind of map it backwards and forwards. Now, obviously, in this model, the important thing is you have to be able to map which stars are on which filament. But in theory, if you could map all of those stars, then you would know, you could build a software model that would show you how, as long as you knew the movement, obviously the direction of the movement, but you'd be able to predict what, for us, the stars would look like in 10,000 years, which would be very different from the classical gravitational software package.
right, exactly, because they're still using for local stars pretty much just instantaneous velocities, and assuming that since there aren't a lot of focused gravitational sources around us, they pretty much put everything on a fairly straight line, at least for the next, thousands of years. Whereas if we are spiraling around, then we should see those.
Yeah, it should start to change. In, 1,000 years is still a long time, but we should start to see quite a big difference. I guess the problem for us is, mapping those stars, almost like creating a catalog of, rather than a star being in a particular constellation, it is assigning them to different filaments and assigning those filaments with particular motions, and sort of the defining how that helical motion connects to other larger structures, which, that in itself is an undertaking. But if we could do that, that would be amazing.
Right.
But as far as I'm aware, no one at the moment is mapping those stars to individual filaments.
Right. Just only the obvious star streams, like where you see a group of stars with radically different motions. That's easy to spot that's a group traveling together, and the mainstream is only they're just beginning to work on that now, really, to match more and more star motions to streams. Eventually, in an EU universe, we should see that all stars have to be mapped to a stream on one scale or another.
And as you say, there is data starting to be collected about the motion of the stars. It's just at the moment when you look at those motions, it seems in some senses a little bit chaotic. But again, it's about having enough of those to map them together to start to see the pattern of how some of these stars would be moving together in a sort of an arced motion. But obviously, our ability to measure their speed at the moment is a straight line. So you would have to be able to measure it over a long enough period to start seeing an arc motion, which at the moment we don't have. We only have straight line velocities for those stars.
Right. And this is another argument against like the Binary Research Institute wanted to make our precessional cycle due to a gravitational orbit where we'd be circling another star in that same time period, 26,000 years. That one is easier to rule out because then we would have to detect our direction of motion, would have to do a complete 360 in that time period. But if we're spiraling along a filament, then depending how tight our helical spiraling is, you see that the more it's axial, the less change in direction we're going to have in the short term. compared to distant objects. And that's the issue. Like if we're very slowly spiraling along as we travel a long distance down the filament, we're going to see that as very little change in the solar apex direction over time. So that's how you know that that's the better model than us circling a nearby star in the same time period, for example.
And where are we on knowing that change over time? The apex, the sun's apex.
See, unfortunately, there's still a lot of slop in the mainstream data on there in that, or not. A friend of mine actually sent me information showing the changes in the measured solar apex direction even from years ago, and the problem is they interpreted that as that the early measurements were wrong and we've got better data, rather than assuming that there could actually be an actual change. And the problem is when they first started getting the solar apex direction, they only had it narrowed down to, like a 10-degree range. And then the problem is if that's all you've got for a range, and you can't obviously detect a change in our sun's direction of less than 10 degrees. If you only know the sun's direction to within 10 degrees, and that's the problem. For what I suspect is they actually were measuring a different apex direction, and that kind of got masked over time. That those old measurements were wrong. We've got better data now, rather than
can't possibly be right.
Right.
Let's ignore it.
Right, like they did with the observations of Sirius color being red.
Yes.
Like, nope, that can't be right. Therefore, we'll ignore those observations. But
there was stories.
Yeah, I suspect we actually will be able to see changes. But again, you have to have that solar apex direction down pretty darn accurately in order to see that, measure any changes in it, and we still don't really have that.
Yeah, so we still have to wait. We can either go back and you can see the old data with the new data, but then the question is whether that old data is correct, or we have to wait for enough time or more accurate measurements. But even if we get more accurate measurements, then they'll still say that the slightly younger data is not as good because we've updated our measuring. I guess that's always going to be the problem.
Right. Yeah, again, there's always that error of matching the observations to the theory rather than the other way around.
Yeah. Okay, so next question is from Matt, and he says, do you think that the pyramid builders understood this whole concept and hence why they are connected to the Pleiades?
Yeah, see, that gets almost into the more esoteric part of it, but once you accept that even the name for the Pleiades and the constellation Taurus comes from that, then you're almost forced to the conclusion that not only do they know the long-term motions, but to have a name like Taurus means that they actually understood the mechanism, and then you open up that whole can of worms that they actually had to have had all this knowledge at that time.
Yeah, so I think that's a very interesting avenue for people to explore, the whole connection with this concept and evidence that ancients did know about this is something that is definitely worth further exploration.
Right, and that's why there I kind of defer to people like Chris Dunn's work, since he's done a good job of showing that, not the whole idea of what the pyramid was done, but just the techniques used to actually build it, how advanced those had to have been, and that's a better place to start with I think with that idea of ancient people having that knowledge.
Well, and as you said, I think the whole thing coming back to Hamlet's Mill, you know, the evidence that is encoded in some of the stuff that we sort of take for granted, that may indeed also point to this connection with this sort of emotion. You know, and again, if there are people, you know, who are very much into this, then you know, I would urge them to start researching that and, you know, get in touch with us.
Yeah, for sure on that.
Yeah. Okay, so moving on to the next question. So next question is from Jonathan, and he basically, again, this idea that if we're moving in the helical spiral, are there any other stars other than Sirius, because in theory there should be, which effectively are stationary from precessing?
Right, and the idea again is if we were traveling on a perfectly straight helical filament, then all the stars on that filament should show that same behavior. But if that filament curves over time, it will only be the stars very close to us that will show that that same correlation that that Sirius does. And in fact, we do have a little bit of the same kind of motion for stars behind Sirius, but we kind of lose the correlation, that direct link to precession. And
sorry, Jim. I was going to say, are there therefore stars like Sirius, but maybe not as perfect as Sirius, so that don't precess as much as they should?
Right. Yeah, that's where that. Yeah, there's other stars behind us in the direction we seem to be coming from, just like Sirius pretty much marks the direction of the sky to within a few degrees of where we were. If you follow back, you'll see that there are other stars just off axis with a motion similar but not quite to that, and that's those are the ones you have to model then onto that Birkeland current.
In terms of understanding the curved nature, how curved, or, you know, because again, at the moment we're portraying this as these perfect curves, but, you know, nature isn't like that. So whether these are perfectly curved or whether, you know, some of them have a slightly kinked structure, I guess may also affect that motion as well.
Yeah, the easiest one to visualize, I think, is if you put stars like on a toroidal path, and you put stars right ahead of us or right behind us, they're going to just appear to circle around. But if you look all the way across the torus, you won't see any correlation. Those stars might just seem to be moving up and down through the sky, but not at all related to, you know, our spiraling through space at that point. They might still be doing the same clockwork motion that we're doing, but it won't be as obvious looking at them that that's what's going on.
Yeah, no, exactly. Okay, next question is from Peter. So he says, so this means the whole solar system, the ecliptic plane, as opposed to just the Earth's equator, is precessing with respect to the background stars. And then he says, I guess we won't notice that our orientation with respect to the other planets stays the same because of the long duration of this cycle.
Right, yeah, it has to be our whole, that was the argument, again, of Walter Cruttenden, that the whole solar system precesses as a unit. And to go off on not too much of another tangent, but since the mainstream notices that now gravity is breaking down on scales of, say, 7,000 AU, or, you know, like a tenth of a light year, that would make perfect sense then, that what Walter basically is telling us is that the whole inertial plane of the solar system is rotating, and that makes sense if you want to put both gravity and inertia not, you know, fixed compared to distant space, but just part of these filamentary structures. The gravity only model, where, you know, like inertia is fixed to to the distant stars, basically. That's our reference frame for inertia. And what Walter Cruttenden found is, nope, it's local, but that fits with the idea that gravity too is a more local effect. And since Don Scott showed that you don't need gravity at all on the galactic scale, then we're back to the ideas of, gravity and inertia being fixed to the local system, which was a pushing gravity idea back from Newton's days, that we have to reawaken that whole idea again.
Yeah, and I think, to be honest, on that one, I think that's one of the things that's sort of next on my list. For me, it's one of those fundamental things to break down, to understand why it is that we do see gravity, and why it might well be that it doesn't really affect things outside of, to use your words, the sphere of influence of the solar system. How do we compare, in particular, when we talked about the fact that this may well have been the stickman figure was something that you saw across the whole sky. Now, obviously, in Peratt's work, that it's based on something that was a much more local event, rather than being an event which happened in the whole of the Birkeland current. Do you feel that's an important thing for this piece of work, or not?
Well, yeah, actually, I think it is important to realize that we can have recorded different events in history from different scales, and the difference between the way to look for it is in those images from around the world, in that if people are all showing the same image from that same perspective, the plane of the torus, with this discharge going across the sky, that's not consistent with a local event. Now, if you're seeing plasma discharge figures from all these different configurations around the world, that would be consistent with a small scale discharge hitting from Earth to somewhere, which would have all these different perspectives. So to the extent that we do see recorded around the world that same depiction of that hourglass-shaped figure seen edge-on from the plane of the torus, that tells you that it's a discharge that could be seen anywhere in Earth, at least at some point in Earth's rotation. They would all have that same perspective, whereas any discharge to the Earth, which is what some people are trying to model, then should have all these different, not even be visible from some places on the Earth, and have all different perspectives than for other people. But
yeah,
to the extent that this particular image is recorded from the same perspective in cultures all around the world, tells you this is a distant discharge seen across the sky, not something that's, that local perspective changes at all. And since it is consistent with our location in the local chimney and what the mainstream knows of that, that's why I would put that one on that scale.
I agree with your view, and because I know that there are other people who've kind of asked about, how does it relate to Peratt's work, and it does in terms of it. There are these figures which are the same, and that's what we are referring to here.
Right, and that's not just, even people like Robert Schoch. He's a very intelligent guy, and he's been studying this, and he would have discharges to the Earth, and that records of them, but I'm not discounting those at all, that there was a discharge to the Earth and people saw that and recorded it. But
yeah, so we're talking about different events,
different scales with different perspectives. Yes.
So what do you see as the kind of future steps for this concept?
Well, one would be to match match the precession exactly to the model that we have this nice helical spiraling on the short period, but then that it goes into a toroidal path, then we better match the motion of the pole at any time to that, and that's a little bit more math. I think that there is enough data to do that, but it's a little more complex math. That shouldn't be too hard, but I haven't done that yet. So,
but I guess also it is at this stage it is about getting people to be aware of it, and then for other people to become involved and to help flesh out, because there's so many parts to this if you think about it that help us to understand our structure in the universe, that this is kind of the start of a long journey.
Right. Just the beginning. I think it's like almost explosive once you start getting enough. Now that there's enough outside the box researchers in all these different areas starting to share their ideas and almost bypass the mainstream model. That's the next step. We're just getting away from an era where all these outside the box researchers are working on their own, putting their ideas out there, and we got to get to a place where all these ideas come together for a more consistent, internally consistent worldview.
Yeah. So I guess it's a call to arms, really. So if there are people who are into this sort of research and want to kind of pick up some of this and do some research into whether it's the ancient cultures, whether it is to do with the petroglyphs, and whether it is to do with star motions, then let us know, and we can kind of help you to start to help us to build that community, I guess.
Yeah, that's exactly right.
Yeah, because there's a lot of work to be done. And that brings us to the end of the Q&A. If you have further questions, then please put them down in the comments below, and we'll do our best to answer those. In terms of future videos, my plan is to come back to this sometime in the future once we've gathered some of this data and we have a clearer understanding of some of those filamentary structures. If you want to get involved, then please drop me a line and explaining how you want to be involved. There are many different aspects in the research that still need to be fleshed out, so the more support, the more help we get, the better with this. As always, be brave, be curious. The truth is waiting for us. Until next time.